punya. Okay, follow the next one. EMJ32304. Tahan ya, atas kehadiran yang awal semua. So untuk polytronics yang kita belajar sekarang ni, Muhammad Aden dengan Abdul Syakur isi ya?
Yes, Doctor.
Okay. Aden, are you here? Silent. Dia pun puasa kot. Can mulai lah. Okay, never mind. Okay, I have uploaded the materials that we learn now. Is not only for our examination. Okay, we learn all the materials during our university time here. Is for the usage throughout our lifetime. So what is polytronic and why we need to learn polytronic? So we have to have you, even though you learn engineering here, you might not end up your life as a career as an engineer, but it will be used throughout your lifetime because you shall need the information or the knowledge not only for your career but for your application in your life. Okay, what is polytronics? So when we learn polytronics, we are talking about power converter actually. Power converter which convert from one set of
Saya terlog out, internet disconnected. Saya nampak ah?
Boleh Doktor, boleh.
Ini tak voice out tadi. Sorry. Okay, again, the application of power electronics. So we can see that the requirement of power electronics conversion is everywhere around us. Starts from generation, wind turbine, solar panels, down to all the appliances and applications that we use in our daily life. Let's say we have a washing machine. So during wash, the speed is low. During spin, the speed is very high. And so how to control in terms of low speed up to upper and higher speed? So by using power electronic conversion. Okay. So let's say we have a air condition control, or we have a air condition in our car. Doesn't matter in our car or in our home. So how to control the room temperature? There is two way. Manually, let's say we have a manual switch, and so if we have a manual switch, what we shall do is that we shall switch on, and when we feel that the temperature is cool enough, we switch off. So we have only two kind of control, which is on and off. So that is what this kind of curve or pattern is doing. When we have enough temperature, so this is the gauge of enough temperature, means that it's cool enough, but still the motor or the compressor will operate. So what we have to do is we have to switch off. Once we switch off, the compressor will stop and the temperature of the room will drop down. After it enter or reach the minimum or lowest range, we will not switch on yet. So we have to switch on manually. Just to switch on manually, or the sensor will detect the level, it will switch on manually. So it switch on, then switch off here, and switch on here. So you can see that we have only two kind of control, we switch on and off. So this is what the manual or the solid state kind of switch control. So means that the response is not so good. Means that the comfort level of our what we reach, what we set from the control is very uncomfortable. If it's cool, it will be too cold, and if it's hot, so it will be too hot. But if we use electronics, we are able to control in terms of exceeding into extreme cool or extremely hot. We are able to control between the range only. The sensory will detect, and if it's too hot, the it will switch on and off, on and off, on and off. Means that our response is quite fast, and we are able to adjust the control faster and smoother compared to manual or solid state control. So something like automatic control to extreme hot or extremely cold carrier. So this is the advantage of inverter air conditioner versus non-inverter air conditioner. It just switch on and off during when it detects the high limit and lower limit. But when you use inverter kind of control, we just set what our setting. If we set 24, you will see. So it will. Sorry guys, putus lagi.
Brought to you by RealPars. Today, you will learn about VFDs, specifically what they are and when we use them with automation and PLCs.
Nampak dah tu.
Okay, tengok dulu.
Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPars videos. This way, you never miss another one. So what exactly is a VFD? Well, it stands for Variable Frequency Drive. They are used for running an AC motor at variable speeds, or let them ramp up their speed to give them a smooth startup. Some people simply call them drives. They work by adjusting the frequency of the motor to adjust the RPMs. To do this, a VFD will actually convert the voltage twice. First, it converts our three-phase AC to DC. This is accomplished with diodes. Then it cleans the DC with a capacitor. Next, it will convert the DC to AC. This is accomplished with transistors acting as switches. Utilizing these switches is what allows the VFD to adjust the frequency that the VFD supplies to the motor. This, in turn, controls the speed of the motor. Now, I know this is a lot of information to take in. Let me compare the internal workings of the VFD with a simple plumbing system. First, let's look at the diodes that convert the AC to DC. This operates like a check valve in a water system. A check valve, like a diode with electricity, only allows water to flow in one direction. The capacitor acts as a water filter to keep everything clean and usable. The transistors act like valves. They turn the flow on and off when needed. This allows the VFD to adjust the frequency of the motor. Now that we have an understanding of how a VFD works, let's see what they're used for. One very common use in industry is to control the speed of a water pump in a water treatment facility. A water treatment plant typically has a constant flow of water coming into the plant. However, if the water demand exiting the plant is lower than the supply entering the plant, then the operator will need to slow down the supply. This is achieved by using a VFD on the AC motor. The operator can monitor water flow and manually adjust the VFD accordingly. Another great thing about VFDs is the fact that they can be controlled with a PLC. Using basic communication protocols that have been covered in previous videos, such as RS-232 and RS-485, PLCs can monitor and control motor speeds using the VFD. This helps make a process like water treatment that much easier and more efficient. This setup can be used in any situation that would benefit from automation. Let's look back at what we now know. VFD stands for Variable Frequency Drive. They are used for controlling the speed of an AC motor. They are also used for ramping up a motor for a smooth startup, or to prevent a heavy load from straining the motor on startup. This is accomplished by adjusting the frequency delivered to the motor. A setup of an AC to DC converter, then DC to AC converter. VFDs are used throughout industry. A common example is to regulate water flow entering a water treatment plant. VFDs allow the operator to control the flow of the pump manually or automatically with a PLC. There are many different brands and features available. If you're looking at using a VFD, just be sure to do your research. I hope this video has helped you get a feel for VFDs. They really can make any automation or industrial process operate more smoothly.
Okay, that's for the VFD, is a variable frequency controller. And so why I show the video just now, because you have learned on the machine before. So we have learned on the how to control the speed and how to control the speed of machine. Let's say if we have an AC machine, so we can control by changing the source frequency, and because the AC machine will rotate based on the source frequency. If you supply 60 Hz, 50 Hz, rotation will take place or will operate the same like the incoming voltage frequency. But how to change the frequency, that's the VFD comes into the picture. So other than that, the converter is also required, such as we have a source of AC, we want to supply or charge our load, electric vehicles, refrigerator, our entertainment appliance, so we need a DC. So how to convert from that AC to DC? So the converter will come into the action. You can see here, objective of electronics to match the voltage and current requirement of the load. Because the load needs DC, the incoming is AC. And one question, why we supply in terms of AC instead of DC? Why we don't take DC directly from the source or from the generation? Ada sebarang jawapan? Any answer? If we need DC, why we take or we generate DC, AC from generation?
Sebab AC tu datang daripada generator. Good.
Oh, ada. Okay. Any other answer? Betul. Seorang ada sini. Kan ada orang kat kelas ni? Dah tambah dah. Okay. Okay, it's a good answer. Actually, we need or we generate AC because it is simpler and cost. The cost is much cheaper compared to generate DC and converting DC and transporting DC. But we have also advanced technology to convert and transport DC, such that we have now the trial or the station in Gurun. We have DC line, DC link, and DC line from Malaysia to Thailand using DC converter and DC transmission link. But conventional, we have AC, and we have AC. The incoming from, let's say, our dam, Pangan, hydro generation. So we use AC, conventional AC synchronous generator. We convert into higher AC transmission line voltage, and we transfer into in terms of AC, because it will require or it will need such a conventional technology. So means that cheaper compared to DC lah. However, due to some circumstances, DC is much preferable lah. So later we learn about that. But as of now, let's say we assume that the incoming source is AC, but our required load is DC, so we have to put a converter in between to convert the DC AC to from AC to DC. So polyphonic converter here is to convert one type or level of voltage or current into another level of range. So that's why the converter is required. So in terms of classification, so what kind of or type of converters generally we have in the market right now? So it depends on what kind of load requirement that we need at that time, and depends on what are the recent or the current input that we have at that time. And different place, different situation, different scenario, there will be a different kind of input available at the time, and based on our load, so what kind of voltage pattern and level that we need. So that's how we want to set what kind of converter that we need to apply at that scenario. So let's say we have AC input, normal conventional AC input, but at that time we need a DC output. Instead the load require a DC, so we have to put a rectifier. AC to DC converter, or so-called a rectifier, is needed to convert from AC to DC. And so example of a rectifier that we, or circuit that we use for this kind of converter is a half-wave rectifier, the cheapest form of circuit, or a full-wave rectifier, and half-wave rectifier or full-wave rectifier. So we have seen before how the half-wave rectifier composite, which is from a single diode. So means that it will only pass the positive and positive poles or positive cycle. The negative cycle it will block, and the negative cycle will be blocked, only release the positive cycle. So this is the most cheapest or the simplest rectifier, AC-DC converter. It's formed from a single diode half-wave rectifier. Or full wave rectifier, if you need a full wave rectifier, so it will apply or it needs more than one diode. So it means that you might need 4 pieces of diode to convert AC into a DC. So all the topology here, you need to understand, and you need to remember the topology. Then you can extract the formula from that. Same like what you have learned inside our commission before. So the first thing that you need to know and you need to remember is the topology, how the topology looks like. Half-wave rectifier, full rectifier. And from the topology, you can imagine or you can simulate how the flows of the current and voltage. Okay, full rectifier, half rectifier for AC to DC converter. But at that time, if you have a DC already, Means that you have a DC, but you need another level of DC. And you have a DC, but the load need or required another level of DC. So what you need to do is that you have to provide a converter which you can control, instead of, if you have a simple diode here, you might have at least a silicon control rectifier. Means that you are able to control the switch where to on and where to off. Means that if full positive cycle is like this, but if you need a lower voltage level at the load, you might chop down another half of it. Means that only half of the cycle is delivered to the load. Means that instead of full cycles of full wave, half wave like that, you have a quarter cycles like this. Means that if you smooth it out, it become a lower average voltage of output or load voltage you measure at the load. The lower or the slimmer the pulses, maybe the lower voltage you can apply. You can adjust the voltage into the lower form, but you cannot supply more than the maximum, but you can reduce accordingly to the based on the what kind of pulses and duration of pulses that you apply to the switch. Yeah. So that's how the DC-DC converter works. So how to complete or how to provide that kind of converter is by using buck converter topology or boost converter topology or buck boost converter topology. Buck converter is for reduction of voltage. Boost is for boosting or increment of voltage compared to input. Buck boost is you are able to step up and step down of the voltage. So where the buck boost is used, the most common, the nearest application of this buck boost is on your handphone. You can see that your handphone, you have a 3 volt voltage, but the system, it needs 5 volt. And so maybe at full charge, the voltage might come or goes up to 5.5 volt. But when it depletes, it goes down to 3 volt. But the system needs 5 volt. How to maintain 5 volt is by using buck boost converter. At low voltage, it will increase the voltage. At higher voltage of battery, it will reduce the voltage into 5 volt requirement of your circuit. So that is the DC-DC converter. So at some event or scenario, we might need a AC output at the load. We might need a AC output at the load. But at the time, we have a DC input. And this is not DC. This is DC input. We have DC input, but we need AC output. So where we can see this kind of scenario is on the solar panel generation. Solar panel we have, or the coming is DC. But when we want to supply or transmit into the grid line, so we need to transmit in AC. So we have solar farm, so that's why we need DC to AC converter. So sometimes it's known as inverter. So DC to AC converter, seldomly or most of the time it's called inverter. So this sometimes is called rectifier. Rectifier circuit, AC to DC. So DC-DC converter is a converter. And AC-AC converter usually is known as cyclo converter. Cyclo converter. So how to convert from DC into AC is by using half bridge or full bridge inverter. Half bridge means that we need only two less circuit, less component. If full bridge, we need for at least for single phase, we need 4 fully controlled device or power switch. Or we have a we can provide a multi-level inverter to the system to convert from DC to AC. So from AC to AC, we have AC, but we need another AC. Means that maybe the incoming is 50 Hertz. The out going to the system, we need maybe from 10 Hertz starting frequency, maybe up to the more than 50 Hertz, maybe up to 100 Hertz of operation. So how we want to accomplish that is by using cycloconverter or matrix converter. Okay. We shall understand and simulate and the topology later in our simulation and OAL practice. So power conversion can be multi-step process. Means that if we convert, we need DC, but the incoming is AC, so we cannot convert by a single conversion, let's say from AC to DC directly, due to cost, due to the voltage level constraint, and due to some to certain DC, or from DC we rectify from AC, rectify into DC, transmit and rectify into AC, like that. So for example, AC converter can be used to modify any AC, something direct to direct from DC then to AC signal. It depends on the kind of load and depends on the scenario of the transmission or the processing at the time. And so we need a multi-stage conversion. And even though at the end of it we need an AC, the supplying is AC, but maybe at that time the AC source is different level compared to our 50 Hertz incoming, so we have to rectify again. Same, this example is the same like the VFD that I showed you before, because the motor itself is AC. You can see that the motor is AC motor, but the incoming 50 Hertz has to be rectified throughout the VFD. Voltage, variable frequency, and controller. Variable frequency means that we need different frequency. The motor needs different frequency to operate during starting and during heavy load, during light load. So different voltage level and different frequency level, frequency range for its operation. So that's why we need VFD or multi-stage conversion. So if you look further into the converter, so the system-wise, we have source, we have load, and we have converter. But if you look further into the converter, so we can see that the converter, the main parts that operate or function inside the converter is our switch. So you can see here, the black encapsulated plastic here with the metal tag with a hole. So this is a MOSFET, and usually a MOSFET or IGBT. We have three pins extruded from the body. So one is incoming, one is outgoing, one is your control port or control point. Meanwhile, we have here, this is normally a diode, and a diode. We have anode, we have cathode. So it shows you where the incoming and where is the outgoing terminal of the device. We have here anode and cathode. So the lines here usually represent the cathode. So the current flow from anode to cathode. And Terputus line, sorry Kak Mena putus tadi.
Dekat diode.
Okay, thank you. Okay, again we have anode and cathode for diode. So it will allow the forward flow. It will block the reverse current. And we have transistor. So transistor, this is a module of a transistor. Higher current and higher voltage, the component size might be different from the lower small signal transistors. You can see for power application, it comes in a much bigger size of device compared to the small signal devices of diode and transistor. And some more for the higher, we can see later, for the higher voltage and higher current conducting device, we shall have a metal type of device. And at the back of the device as well we have a space to attach a metal heatsink actually. And we shall have a heatsink and to be accompanied with the device. Because when you conduct higher current that flows into the system, so we shall have a losses, power loss. One is the power that we deliver to the load, and we have a source, AC source, we have a diode, we have a load. One is the power that being used at the load. So the power delivered is equal to VI, and let's say the power delivered is VI, or the I square R here. If we measure the load, we can measure the voltage drop across the load times the current that flows into the load. So that is the power that being used by the load. So this is your resistive load, let's say. Or we can, if you know the values of the resistive load, we are able to measure how much the current that flows into the load. So this is the consumed power. But the things that in our concern right now for power electronic device is how much the power that lost from this device. Means that instead of delivering power, how much actually the losses that happen inside the diode. So how to measure the current that lost in the diode is by the same, how much the current that flows into the throughout the line times the, if the diode we are able to measure the voltage drop, and let's say 0.6 volt generic diode, we have a 0.6 volt of wk, and voltage drop across anode to cathode during switch on 0.6 volt means that at any time when the current flows throughout the diode, the voltage drop, if we measure across the diode, is 0.6 volt. Let's say if you have 100 ampere, let's say 10 ampere lah, 100 ampere is too big. 10 ampere of conduction current. So how much the losses at our diode right now? So the equation is that I square times R. So I is 10 square, sorry, not I square R, because the equation now is related to how much the voltage drop. We only able to measure the voltage drop across diode. So 10 P equal to V drop times I. V drop is 0.6, I is 10, so we have a 10 watts of losses is 10 ampere. If there is a 100 ampere, so the losses is 60 watt. And the losses is 60 watt. So our concern now is the the device itself, how much the losses, the performance, or the behavior of the device, and the device, and not on the load actually, on the device. And okay, for our instance of consideration right now, in our simulation, in our topology for the time being, is that we shall consider the losses later, but for the time being, when we want to understand in terms of the behavior or the response of our topology, and the rectifier, inverter, cycle converter, we shall consider that our switch at the time being is an ideal. Ideal means that when the switch is switched on, when it is switched on, and switch on means that the circuit is closed. We have a closed circuit. The connection is fully contact, switch on. So there will be an infinite short circuit current with zero connection loss, and means that there is no resistance. So this is ideal consideration for the time being. And as of now, we consider that for on state of the switch, and on state of the switch, there will be infinite short circuit, means that there will be no resistance happen, and no resistance happen, and no resistance happen at the switch. Means that, let's say just now we consider that the voltage drop on the practical switch, we have 0.6 volt, but now there is no voltage drop across the switch, no resistance across the switch, and it is firmly contact. So that is the on state for the time being, and we consider it like that. If we have a off condition, just now it's on. As of now, we consider as there is a open circuit, totally open circuit. For off condition, ideal state means that it is totally open, and the circuit is totally open. No dielectric breakdown, means that no capacitance between the on and off circuit here, between the two lines. And it's totally on, and is that totally off and totally on. No resistance, no voltage breakdown, no dielectric contact between the two circuits. But later, when we go into the protection of the device, we shall consider that the switch should be considered as a practical switch, no more ideal. For the time being, for simulation wise, we shall consider that the circuit is totally ideal. Means that when it's on, so it is on, and when on, so this is the graph. It can conduct the highest possible current without any voltage drop. So we have here a voltage drop for practical switch, but ideal, there is no voltage drop. The drop is zero during switch on. During switch off, there will be no breakdown voltage. You can apply any kind of voltage reverse of the reversing the poles without breakdown. And means that during on, you can deliver any kind of current up to 1000 ampere of current. It won't short, it won't burn. And there will be no voltage drop. And during switch off, you can put any reverse voltage without damaging the circuit. It won't crack, and it won't crack, it won't damage. In practically, if you conduct the forward current, there will be a voltage drop. And if you switch off and apply higher current, there will be a voltage breakdown. Means that the higher current, the higher voltage you put into the diode, it has a limit. It will break down at certain level of voltage. So, okay, that is the ideal condition. And if we look at the diode itself, so diode is considered as non-controllable or uncontrollable device. So we have three kind of major switches in our photonics, which is diode, thyristor, and transistor. MOSFET, IGBT are all transistor, and MOSFET referring to metal oxide field effect transistor. IGBT is referring to insulated gate bipolar transistor. So both are transistor. So we have thyristor. SCR is thyristor. Silicon control rectifier is the thyristor. We have diode. So this is three major components which are discussed in our power electronic switches. So if you refer to diode, so this is one of the non-controllable or uncontrollable switches or device. So for diode, the on and off control conditions are determined by voltage and current in the circuit. So it means that when we have a forward bias, the current flows from anode to cathode. So the diode will pass the current, I diode. And when it flows back, so the diode will block the current. And the flow of positive or from anode to cathode will take place when there is a voltage difference between VD. So it means that VD is bigger than VC, V cathode. Sorry, VA. V anode is bigger than V cathode, so there will be a flow of current. And when VK is bigger than VA, so there will be a reverse bias. And so forward bias when the current positive and reverse bias when the VD is negative. Okay, there is important dynamic characteristic of a non-ideal diode. For ideal diode, the voltage drop or forward voltage drop is 0. You see, like I told you before, we have a voltage diode V forward of 0.6 for normal diode. Maybe for Schottky diode, the voltage drop is much lesser. The lesser or the lower the drop, the better the diode. But the higher the cost of the device. So important dynamic characteristic of a non-ideal diode is a reverse recovery current. So when the diode switch on, means that it conducts. The current in the diode will increase. Sorry, it will decrease. When turned off, it will decrease and it will swing before comes to 0. So during switch on, so this is on state. You can see here, this is on state. This is off state of the diode. So this is the gap between on and off. So when you switch on, non-ideally, there will be a voltage drop of 0.6, and because it at 0.6 for this time. And the current will flow, let's say at 10 ampere. It depends on the load and on the capability of the diode. Let's say we assume that we have 10 ampere of conducting. Once the we switch off, so we shall measure that the voltage reverse across the diode. We have a diode, so VR here. We shall measure the voltage across the diode. There is a reverse voltage. But before the current turn into 0, by right, this 10 ampere, once we switch off, it down to 0. But it will swing down first. So this is the reverse recovery. Before it return to 0 line, it will swing down. And dia macam ada what so called panggil apa? Dia ada spike. There will be a spike. A spike. It will spike to a certain level, then it goes down to 0 current. So this, how long it takes from the time in reverse from the peak negative down to the 0 is so-called a reverse recovery time. The higher the shorter the RR here, T of reverse recovery means the best the diode is, and the higher the response, the faster the response, so the best diode or the better the diode characteristic is. So means that when you want to choose a diode from the market, so this is one of the criteria. It's not the only criteria, but it's one of the criteria how to choose the best diode. Means that when you want to use diode in a higher frequency response, so the TRR here should be the shortest possible and duration you should choose, because if it takes too much time to recover, so you cannot use in a higher switching frequency. So you can see here SIC and Schottky are the best because it has the most fastest TRR. Means that if you have a higher TRR, so this portion as well will contribute to the losses of your circuit and losses of your circuit. So you can prove it later through our simulation in our OEL or in our lab modules to come. So this is characteristic of our diode. And so ideally, it will on and off, and it will on and off. But actual, practical, we have a voltage drop, and we have a voltage breakdown, and we have a time reverse recovery issues of the diode. So you have to take care for your design criteria. Okay, semua okay kan setakat ni?
Okay, sir.
Okay, sir.
Semua okay. Oh, you want to take 5?
Take 5, sir.
Continue. Kita
Take 5.
akan habis kelas dalam awal sikit, dalam pukul 12 suku ni tu.
Continue.
Nanti pukul apa? Continue ah. Okay, sekejap. Pukul 12.30 kan? Pukul 12.10 kita akan habis lah. So for this evening, I will upload there will be no synchronous. It will be asynchronous. I will upload the materials pre-record. I hope you can view by your own. And at the end of the session, I will have some quiz or question. You just answer inside your Google form and submit. I want to test your understanding on the chapter that we have gone through. Okay, we continue. Okay, just now we learned on the diode. If you have any question or concern, just highlight, write out. We shall review again. So for thyristor, it is some sort of 3-terminal device. As you can see, 3-terminal device with a metal tag. So anode, cathode, and this is our gate actually. So thyristor is a controllable diode. It's a diode composed of anode and cathode here, and with a gate, So this controllable gate, some device we just apply current. Some device we need a voltage as a control signal. Some device we need current pulses. Some device we need voltage pulses. For SCR or silicon control rectifier, we just apply current and current. So we have triad. So this is families of thyristor and thyristor. We have triad. We have GTO. Outside point of view, physically view, all the components look like this. Three terminal device like this. But in terms of the topology, so SCR, GTO, MCT will represented by several kind of drawings to differentiate between all the devices. But physically, if you buy from the market, the body of the components all are the same, like this. So, capable of conducting large current, and large blocking voltage. So the current and the conduction when you put IGT. So this is the characteristic of SCR or thyristor. It can go higher voltage and higher current compared to MOSFET and IGBT and compared to transistor. This is thyristor. But in terms of frequency, it can only tolerate line putus ke tadi?
Ya, line putus.
Putus kat mana tu?